Welcome to 1.6 Uncertainty and Measurement. So we know that different units are available, right? We have temperature, we have grams, but how do we use that information? And so when we think about collecting measurements, what are we going to do? How can we use that? And we're going to talk about the uncertainty. So what does that mean? If you get on the scale, or if you go to an older supermarket where they have a basket scale, there's a dial perhaps, and that dial is going to move around. This is different than if you get on a digital scale or a scale that you would use in a chemistry laboratory. So what does that unit mean? And so what are we learning here? So when we collect measurements, we can have accurate or precise. Accurate in this case is going to mean getting the correct answer. So when we think about accurate, it means that you got the right answer. So precise in this case means all of the measurements are similar. So when we look at these two targets, when we look at the accurate, we can see right here in the center that all of the darts, if this was archery or something else, they're all clustered in the center. They all went where you were trying to go. Over here in the other one, on the precise one, they're all clustered together. They're just not where you were shooting for if you were aiming for the bullseye. So when we think about the difference between accurate and precise, we often want to get something. And the way we want to use this is we're going to start to add numbers together. We want to make sure that we're not using too many numbers or not enough. So if we have 6 bananas, you're at the grocery store, you can use a basket scale, which is often the thing found in a grocery store in the produce department. Your recipe says you need a half a pound. It gives you roughly a half a pound. The digital scale says that you have 5.32 pounds as opposed to the 5.1. Neither of those are wrong, but the digital scale is going to be more accurate because it has more decimal places. So the fact that this number has 3 places after the decimal versus the 2 places in the previous number. So accuracy is often thought about how many more digits you get. So uncertainty. Now, when we think about the basket with the bananas, those numbers were pretty close. So if you use an analog thermometer, the kind where the mercury rises, although here in this day and age we don't use mercury, they use the red alcohol. You're going to look at that and you're going to kind of read it, and there's always the part where you're like, I think it says 98.5. Or maybe you think it says 98.7, to where you've looked at the different hatch marks. And so if this is a thermometer and there are some hatch marks here, and maybe the mercury or the red alcohol goes right here. And so you're going to guess. You're going to look at these and you're going to make a guess. So when we think about the uncertainty, we're asking, how much are you going to guess? So most of the time in Gen Chem 1 lecture, we're not going to be doing a lot of guessing, because I'm going to tell you, you weighed out 12.8 grams, or we're going to talk about a value. And so this is to make sure that there isn't additional significance. So when we add two things together, when you plug it into your calculator, it's going to add all the decimal places. Your job to use the uncertainty is to determine how many digits you should give. So significant figures. All of the numbers on a scale are significant. Or all of the values in a problem. On an exam, on a weekly assignment, on ALEKS, all of the values in a problem are significant. So the estimated place means you can only estimate one place. So if I said, do you have a penny? I'm probably asking for 1 penny. But if I'm looking at something and it's roughly $5, that means it could be really anywhere from $4.75 to $5.25. That's kind of roughly $5. So when we estimate, which we're not really ever going to do in Gen Chem 1, in the lecture, in the lab or in a lab-based course, you will often estimate a place. So to determine the number of significant figures, all non-zero numbers are significant. That would be the number 1, 2, 3, 4, 5, 6, 7, 8, and 9. To be honest, those numbers make a lot of sense. It's the number 0 that is difficult because zeros between non-zero digits are significant. Zeros at the beginning of a number are not significant. Zeros at the end of the number are significant, but only if there's a decimal place. So the hardest part of this is, what about 0? Okay, so let's work on counting how many significant figures these digits have. So in the first one, there are 3 zeros. So we can look at these values, and so I'm going to use a highlighter to highlight the significant digits. So in this case, we see that there are 3 sig figs. And I like to abbreviate SF in this case. So there are 3, because the 2 zeros at the beginning, these 2 up here, are not significant. Now what about this one? There's in fact only 1 sig fig, because there's no decimal point down here. So no decimal means tailing zeros are not significant figures. So we tend to think about leading zeros, which you saw in the first example. Tailing zeros are not sig figs. If you are ever working a problem or working on an exam, I think that using a decimal point at the end can be kind of confusing. Now, Alex loves it. It thinks it's important. It will also have you put it in places where I might not have recommended. So if we look at the third one, there are 1, 2, 3, 4, 5, 6. So we have 6 sig figs. The homework system we're going to use would have actually asked you to write this 7, 1, 2, 3, 4, 5 decimal to imply that it is significant. Traditionally, you do not need that decimal place. That is implied. So significant figures kind of make a lot of sense. So the way I like to really think about significant figures is about monies. So I did say monies. If I told you that you have this value of money, so we have 2 zeros, 1, 2, 0, 0, 0, 3, 1, 7, 5, 0, 0, 0. Now, depending on where you place the decimal point, which I will now add in green, it matters how much money you have. If we put the decimal place here, you have 12 cents. That's not very fun at all. But what about if we added the decimal place here? So on the red one, you now have lots of money. We'll just say lots of money. The thing is, and the reason I talk about this, is that these zeros up here don't change the money. That's why they're not significant. But the ones out here at the back, these can change. The value. The ones up here at the front, they're just placeholders. So that's the way that I like to think about the difference. And the ones here in the middle are always going to be significant. So now we want to think about using them. So in Gen Chem, we're mostly going to do addition, subtraction, or multiplication and division. So the number of significant figures in the data controls how many are found in the answer. So addition and subtraction. The result has the same number of decimal places. Now that's the trick. Decimal places as the measurement with the fewest decimal places. So in multiplication and division, the question becomes, it's about the total number. So the result contains the same number of significant figures as the measurement with the fewest. So in addition subtraction, the total number of significant figures can change. Because if you add two values together or you subtract them, you could lose a placeholder, okay? So you could go, if 10 minus 8, the value is 2. So that only has one significant figure, but they have the same number of decimals. So it's less about the total, but more about what happens after the decimal place. When we multiply, it's the same number. So let's look at some examples. So if we want to add two things together, so 12.58 plus 9.12. So we're going to add 1, 2, 3. We're going to add these two numbers together. So 12.58 plus 9.123 gives us 21.703. Now, I like to think about the fact that we're going to clip it off after the end. So our final value in this case is 21.70. So that's how you would add them together. If we were to multiply those values, 12.58 times 9.123, in this case, 12.58 times 9.123 is going to give us 114.76734. Now we need to trim this back with some significant figures. So both of these values have 4 significant figures. So this is going to give us 114.8. In the next slide, or the next slide, we're going to talk about rounding. It is the next slide. So rounding. There are a variety of different rounding rules that different scientists like to employ. They are all valid. In my class, and in Alex, we're going to use a pretty traditional rounding scheme. 4 and down, round down. 5 and up, round up. So they pretty much round up and down. So other things you might need to know. The rules for normal mathematical equations apply. So if you're using an exponent and you're adding and subtracting, the value at the least significant digits controls the answer. If you have exponents, we will almost never add them, but we will use them in multiplication and division. There are ways that you can do that calculation by hand. My recommendation is to put it into your calculator and allow the calculator to move the exponents for you. So, in our examples, we have a student who weighs out 2 samples, 21.8 grams and 1.297 grams. What is the total weight of samples? So we're going to take our 21.8 grams. We're going to add 1.297 grams. And in that case, we are going to get 23.29. Nope. Hold on. 23.097 grams. And then we need to do our sig figs. And so we are going to clip this off after the shortest one, which means we have one significant figure after the decimal place. And so we're going to get 23.0, but we need to round. So it's going to be 23.1 grams. So in this example, we want to calculate the volume of a box with our 3 values, 15.5, 27.3, and 5.4 centimeters. So we're going to take 15.5 centimeters, multiply by 27.3 centimeters, times 5.4 centimeters. When we plug this into our calculator, you should get 2285.01 cubic centimeters. Now we need to pair back our significant figures. This 5.4 is going to control that since it was multiplication. So we just get 2, which is 2,300 cubic centimeters. In significant figures, that would be 2.3 times 10 to the third cubic centimeters. Oops, hold on. That's the end. Thank you.